All right, this is the last section in Chapter 15 that we are going to cover. 15.9 is called Stokes Theorem. And last time when we were doing 15.7, it was called the Divergence Theorem, and it was a 3D analog to what? Do you remember? Green's Theorem. And we have the same sort of thing going on with Stokes Theorem. So let me actually make the mention of that to start with. So Stokes Theorem is the 3D analog to this one that we'd had before over our closed simple curve. Which was one version, this equation is one version also of Green's theorem. Involving cross products. Okay, so this is where we're headed into. I haven't actually given you Stokes' theorem yet, but that's what Stokes' theorem is going to do for us, is make a 3D analog to this equation. This version of Green's theorem. All right, so we're going to get started right in with that. Theorem 8.1, which is Stokes' theorem. And it says the following: suppose that S is an oriented, piecewise smooth surface. With unit normal vector N, bounded by the simple, closed, piecewise smooth. I think that's enough adjectives. Bounded by the simple, closed, piecewise smooth boundary curve delta S, having positive orientation. Let the vector field F of x, y, z be a vector field whose components have continuous first partials. Okay, continuous first partial derivatives. In some open region containing S. then the single integral over the boundary of S, delta S, of our vector field of x, y, z with the dot product of dr is equal to the double integral over the vector over the region S of the cross product with the gradient dot the unit normal, or dot the normal, the unit normal vector in ds. And again, you can see the analog from back over here. It's a single integral on one side, the double integral on the other. With one side split out a dot product. We've got a cross product with the dot product of the unit vector k over here, which was 2-dimensional, and this is the one in 3 dimensions. All right, so an examples in order. Does everyone have that written down at this point? All right. We're going to use Stokes Theorem to compute the double integral over S, the gradient cross product of the vector field dot the unit normal vector over ds. And the example that we're going to do is the following. S is the portion of the tetrahedron bounded by x plus y plus 2z equals 2 in the coordinate planes with z greater than 0. The unit normal n is upward, and our vector field F has components z, y to the 4th minus y squared, y minus x squared, and z squared. Okay, so this is the problem we're working with. We're supposed to be using Stokes Theorem to compute this, which must mean that we're going to be using the other side of Stokes Theorem to make the computation. So what we're going to be doing is we're going to be looking at the boundary of our region S, or our surface S, instead of the surface itself. So take a look at how S is described. It's the portion of the tetrahedron bounded by this equation, which is a plane, and the coordinate planes themselves, so those are x equals 0, y equals 0, and z equals 0. And of course they're telling us that z is above the xy plane. And then we have this function that we're working with. We'll get to that part in a minute. But we need to talk about the boundary of our region, because that's what we're going to be integrating over is our boundary. So we need to talk about what in the world delta S is going to look like. Okay, so we've got this tetrahedron. Tell me what you got. I mean, the tetrahedron, what is the boundaries of the tetrahedron? What does that look like? What does a tetrahedron look like? Let's just take a step back. It's a triangular-based pyramid, right? Okay, so it's not square-based pyramid, but triangular-based pyramid. So what are the boundaries of this triangular-based pyramid? Those are the corners. How are the corners connected? What do you have, Tally? The origin is part of it. It's one of the corners. The plane is the boundary, but I want the boundary of the region, like more than just the plane, because you've got 4 planes, right, that are bounding it. So so you've mentioned the corners, right? How are the corners connected? How do we connect one corner to the other corner? Line segments, right? The line segments are creating the boundary of this shape. Are you with me? It's the line segments that are doing this. So our delta S is the triangle with vertices. And so what are my vertices of my triangle? Some of you have already mentioned it. Tally, you mentioned the origin, 0, 0, 0. What else? The base. One of the coordinates of the base is going to be at the origin. 2, 0, 0 is correct. And there's one more. Yes. And Caleb, since you're the only one who's answering that out loud, tell the class where those are coming from. What did you do?
The plane.
Okay, the plane when z equals 0. So this equation right here, we're in the xy plane, right? So z is 0. And then where do we get the places where it's crossing the x equals 0 and the y equals 0 line? So these are the 3 vertices. Very good. And this is made up like we said, of line segments. This is 3 line segments. And we're going to give them names C1, C2, and C3 just for a moment, and then we're going to have to figure out what C1 and C2, C3 are. All right, so you're thinking 2-dimensionally, right? Because we're in the XY plane, and I think this is more or less the shape, not drawn, of course, in any sort of a ratio that you have, but in some sort of sense that we were looking at before. So this was the picture that we were thinking in our heads. Okay, so far so good? All right, so I want to go, and we're in 3 dimensions, but I want to go from, I need a different color. Let me use this one. That'll work. I want to go from, let's make C1. We're going to let C1 to go from 0, 0, 0 to, there's no specific way that I'm doing this. This is just the order that I wrote down when I did it earlier, to 2, 0, 0. So in terms of my 2-dimensional picture, I'm going from here to here, right? So this is C1 down here. But we need this to be done in terms of parameters. We're going to parameterize the curve. So my curve itself, I need to take a look at the individual points, and I want to do parameters. What do you think we're going to have? What's it going to look like? X equals, Y equals, Z equals. What are we going to have? In terms of a parameter t, and we need bounds on t as well. Think easy.
2t.
X equals 2t, that would work. And now I can't use my notes anymore because you chose something different. So we'll do it, it's good. You're letting t go from 0 to 1, right? Okay, so what will y equal and z equal? 0, right. All right, curve 2. We're going to go from where we ended. So we're going to go from 2, 0, 0 to where? Right up here, right? C2 is up to there. So 0, 2, 0, and we're going to parameterize this again. So since we've already let our t go from 0 to 1, let's continue to have that pattern, okay? So that we'll stick with all of them being the same, so don't have to do them separately. So what would x equal? How am I going to go from 2 back to 0? Two minus t. I don't think that's going to quite get me there, but you're close. 2 minus 2t will work, yes. Right. We've talked about parameterization before. If you need to see more details on how to get there, that's fine. You can kind of reason through this one. We need to be starting at 2, and we need to be getting 0 at the end. Okay. How about y equals? That's 2t. It's just like the x equals on the earlier one. And then how about z equals? 0. Our last one, C3, goes from where we just ended, 0 to 0, to where? 0, 0, 0. And again, we'll let our t go from 0 to 1. I'll do the hard one, z is equal to 0. What else? X is also equal to 0. And then y looks an awful lot like x from the previous curve 2, right? So it should be 2 minus 2t. Now, I will say another option, you would not have to use these parameters. We've talked about this before, but just as a reminder, we don't have to use the parameter 0 to 1. It's kind of friendly, so we kind of like it. Which you could have used the parameter from 0 to 2 pretty well on this one, since we've got all the coordinates ending at 2's as well. And then you wouldn't have had the 2's in all of these. So if I had let my values go from 0 to 2 here, then each of these places where I had 2's would all be 1's, which would be fine too. Okay, so we've got 3 curves, and we're going to be finding, let me go back over here to this equation to remind you. We want to find the integral of the dot product along each curve. Well, we've got 3 curves, so we're going to do 3 separate integrals. Okay? But the integrals are all fairly clean because the curves themselves are line segments. They weren't very complicated curves. So that's where we're going to be headed next. All right, so we're going to do an integral along the closed simple curve C1 of the dot product of f with dr. So I don't have f on this particular screen. Let me actually just write it up here to remind us, since we're going to be referencing it. It's z y to the 4th minus y squared, y minus x cubed, and z squared. Okay. All right, so this is over our curve C1, and we have each of these components, and then the dot product with dx, dy, and dz respectively. So we have, I'll just write it down the way that they have it written for us before too. This dx plus the middle component y minus x cubed dy plus z squared dz. And if you go back real quick to the previous slide on the curve 1, we can actually find dx, dy, and dz. We didn't actually do that before. So dx would be 2, and it's dt. Dy would be 0, and then 0 down here. So what we end up having is we end up having only the first part, because these are both zeros right here, right? This is 0, and this is 0. So those components aren't going to even matter whether we take them properly or not, because I'm going to get zeros there. I will do so, but just to sort of be aware that that's what's happening on this particular one. All right, so if we use our components for what z equals and what y equals, we end up with y equals 0, z equals 0, so this is 0 minus 0. And dz is, or sorry, dx was actually 2, right? Y was 0. X is actually, was it 2t? 2t cubed, but then this is times 0. Plus, and then this is 0 times 0 at the end. All this is dt, because I've put everything in terms of t's now. What do I end up with? Yeah, so this is the integral over t from 0 to 1 of 0 dt. And when I take the integral of a definite integral, well, if it were indefinite, I would get the value of c. If it's definite, then if I evaluated the 1 and the 0, I actually end up getting 0. So this is 0. So the first one gave me nothing. The other two actually give me values, so don't think that this is all just going to dissolve into nothing on like some of them do. It won't. I'm not sure I have enough space on this slide for the next one. It's a little bit longer. So let me go to the next slide. Are you good with that? Does everybody have this one written down? All right. The next integral goes over the curve C2. So keep in mind, I just changed the formulas, right? We're on C2 down here, so let's actually write these out. What would dx be? You know what, let me change the color just to distinguish it a little bit. What would dx be? Sorry, go ahead. What was it? Negative 2 dt? Yep. How about dy? 2 dt and 0 for dz. Okay, so we're not going to have as many zeros this time. Okay, so our integral on this one over C2 of our function z y to the fourth minus y squared dx plus y minus x cubed dy plus z squared dz. All right, so our integral in this goes between 0 and 1. What was z in this one? It was 0, right? Y to the fourth is actually not 0. It's 2 minus 2t. Or is this one just the shoe t? 2t to the fourth minus 2t to the fourth dt. I think I left a parenthesis out. Let me get that back in there.
2t squared.
Oh, thank you. This fourth was on our previous one. Perfect. Does that look okay? The y was 2t. X, that one is the 2 minus 2t, right? Cubed. What's dy? I don't think I put this in right. Nobody caught that one. Right here. Oops. I meant to have an eraser. What was dx? It was negative 2 dt, right? All right, and then dy is 2 dt. I'm missing another parenthesis right there. And then the z is 0, and dz is 0 dt. So it just disappears at the end. All right, so some of this goes away. That's 0. Negative 2t to the second would be negative 4t squared. Oops, and then I'm supposed to multiply it by negative 2, so how about we change that to just 8? 8t squared dt. Is that okay? Can I put the dt's at the end? You guys good with that? Okay. All right, the other component is a bit messier. Yeah? Because you have 2 minus 2t quantity cubed. So let's jot this down here at the bottom. And then when I'm done with that, it's actually going to be multiplied by the 2. Well, 2t minus this and then multiplied by the 2. So multiply this out. Tell me what you get. Do some
24t plus 24t squared minus 8t cubed.
24t and then what?
Plus 24t squared minus 8t cubed.
That looks right. Did anyone else finish foiling all of that out, distributing all of that out? Okay, we'll go with it, Caleb. Nobody's complaining. All right, we're supposed to have 2t, let's see, 2t minus this. So 2t minus this quantity right here, which is going to give me negatives on everything, right? So I'm going to have negative 8. I'm going to have 2t plus 24t, so this would be plus 26t. And then minus 24t squared plus 8t cubed. And then all of that should be multiplied by the 2 that's appearing right here. Everybody good? So I have negative 16, positive, what is that? 52t, negative 48t squared, positive 16t cubed, dt. And then, of course, a couple of those combined before we have to integrate and evaluate. Negative 40t squared minus 16 plus 52t and plus 16t cubed dt. All right, so we need to integrate, and then we need to evaluate from 0 to 1. So the good news is, although we've been dealing with lots of 2's all the way along, we only have to evaluate the 0 and the 1 now because we chose that as our limits of integration, or our restrictions on the parameter. All right, so somebody tell me the integral we're going to get. Okie dokie, I'll get us started. Negative 40 t cubed. Somebody else, keep us rolling. What's next? Just for fun. All right, 16, negative 16t plus, good, 26t squared plus 4t to the 4th, evaluated at 1 and 0. 1 is fantastic, 0 is even better. So we have negative 40 thirds minus 16 plus 26 plus 4, right? Well, with the exception of the negative 40 thirds, I was good, but somebody grab a calculator or add those together for us, and we'll double check to make sure we have the same value. I don't think so.
I got 2/3. Yeah.
2/3 sounds correct. Did you have 14 minus 40 over 3, James?
It's subtracted. That's what I got.
Oh, okay, gotcha. Good. And so you had 2/3, Caleb? Fabulous. So this one's 2/3. So the first value is 0. The first curve is 0. Second curve is 2/3. But we have 3 curves. So now we're doing one more integral over the curve C3. This one's going to be more like C1 because we had parameters that had zeros in a couple of places. So this is f dot dr. Our third curve, C3, okay, zy to the 4th minus y squared dx plus y minus x cubed dy plus z squared dz. And the curves that we're looking at from back on the previous slide, let's see if we can get to the right one. We're down here at the bottom. So what is dx? 0. dy? Negative 2 dt. And dz? 0. So for all intents and purposes, dy is the only one that we have. So let's cut to the chase on this one. I was trying to show you out some details of the things first. But because this one's 0 and this one's 0, those are going to go away, right? They're not going to exist. So we actually only have the curve over C3 of the middle part right here. This is the only part to have concern for us. And then we'll evaluate this piece. So this is the integral from 0 to 2. Y was 2 minus 2t. Oh, I'm sorry. Yes, it is. 0 to 1. 2 minus 2t, x is 0, right? And dy is negative 2 dt. So we have negative 4 plus 4t dt. So go ahead and integrate this one. Evaluated at 1 and 0 gives me a whopping total of what? Negative 2 is right. So we've actually done all the hard work. The only thing to do now is to answer the question. So the question was, what is the integral over S of the gradient cross product with the vector field F, dot with a normal ds? And it's the sum of the 3 above integrals. I'm writing this down just to remind you, not because you need to write that piece down, but that's where it's coming from. So the first integral was 0, the second integral was 2/3, and the third integral was negative 2. What's the total that gives us from these three? It's negative. Negative 4/3 is right, Nathan. Very good. And I think there's 3 of these that you're going to do like this one. One of them is even a tetrahedron. So. All right, one other type of directions we're going to take a look at today. And it's going to be using the theorem the other way around. So we're going to use Stokes Theorem to evaluate the integral over C of f dot dr. Our curve, oh, this is not 2, this is 3, this is 2. C is the boundary of the portion of z equals 4 minus x squared minus y squared above the xy plane, oriented upwards, and f equals x squared e to the x. Okay, I'm not going to have space right here. Let me move it down to the next line. X squared e to the x minus y. Second component is y square root of y squared plus 1. And the third component is z cubed. All right, so one of the things that we need is we need to do the gradient cross product with f. Okay, so this is the other half of the Stokes theorem that we did before. So what does this look like when we do the cross product? I just graded some of your papers doing these things. So what does this look like? What do I set up? Matrix, ijk, right? And then what's the next row? All those deltas. So del x, del y, del z of and then the vectors, right, below them. So this is x squared e to the x minus y, square root of y squared plus 1, and z cubed. All right, I want to volunteer to tell me what the first one is going to be. That's going to be dotted with j, or times j. I.
0 minus 0.
0 minus 0. Fantastic. Okay. How about the second one? This one's subtraction. A few of you forgot that piece on this on the stuff you were working with. What about for j?
0.
It's also 0, isn't it? So that's friendly. The next one's not 0. It's -1. So it's 0 minus 1, okay. So I end up getting the vector what?
No, 0 minus
It's 0 minus -1.
Oh, I'm sorry. You're right. Yes. I got ahead of myself. Not enough negatives going on. Excellent. All right, so what is my vector that I end up with? 0, 0, 1. Fantastic. So this is actually, and it says it's oriented upward. The oriented upward tells me my normal vector, n. So what is my normal vector n going to be in this if it's oriented upward? It's a unit normal. So what would oriented upward look like? Think about the components. There's 3 components for a vector. It's going to have a z component only, right? Because if it's going upward, then the only thing it's got for a component is a z component. The z component, so these are going to be both 0. What would the z component be? 1. And why would it have to be 1? Because it's a unit vector. Okay, so this is coming from the fact that it's oriented upward. So you might just jot yourself a note here that this is because it's oriented upward. That's giving us the unit vector, the unit normal vector. All right, and we need one more component that we haven't done yet, and that's ds. And ds would end up being 0 squared plus 0 squared plus 1 squared dA, which just gives us dA to start with. I think I have enough space in one line on the bottom of the screen to finish this problem out. So this is the what we're looking for is the integral over c of f dot dr. This is the double integral of 1 dA. And we're going to turn it into polar because that's friendlier. From 0 to 2 pi. 0 to 2. Okay, going back up to the z equals up here, right? Zero to 2 pi, 0 to 2. Of dr d theta. Which ends up being the integral from 0 to 2 pi, of course, of 2, because we would get, oh, I'm sorry, you're right, yes, I missed a r. Thank you. Oops, there we go. All right, so this is the integral from 0 to 2 pi then of what? R squared over 2, evaluated at 2 down to 0, d theta. I don't quite have enough space. What is this going to give us? 2, right? So then I've got the integral from 0 to 2 pi of 2 d theta, which would be what? 4 pi. Going to be 2 theta, and 2 theta evaluated at 2 pi gives me 4 pi. Of course, evaluated at 0 gives me nothing. So it collapses down to that. And I've got 2 problems that I'm going to have you do from this particular set. So here's the homework. It's page 1060. Problem numbers 5, 7, it's not 5, it's 6, 7, 8. 6, 7, 8. And then 12, 18, 20. Can't remember where 12 falls, so maybe it's 4 in the first set and 2 in the second, or maybe it's 3 and 3. Okay.